In this video, we'll discuss the principles of photolithography. In an earlier video, we explained that the fabrication process of microchips is an iterative process. It consists of major steps such as deposition, etch, doping, and photolithography. Here, we'll provide an overview of the lithography step. The word lithography is derived from lithos, meaning stone, and graphene, which means writing. The standard lithography techniques are categorized into direct writing and imaging technique. A prime example of direct write techniques is the electron beam lithography, or EBL. In EBL, the electron beam can be thought of as a nanoscale painting brush and the wafer as the canvas. As such, the nanoscale electron beam is printing features one brush stroke at a time. The beam is guided by an electronic design file in an EBL. The nanoscale dimensions of the electron beam make EBL suitable for printing nanometer-sized features. However, this technique is slow compared to photolithography. Therefore, it is mostly suitable for performing lithography in research settings. To overcome this shortcoming of direct writing, an alternative paradigm is the imaging techniques. This class of lithography techniques use light sources such as ultraviolet or extreme ultraviolet that can print features on large portions of a wafer in one exposure. As a result, these techniques provide high throughput and are suitable for manufacturing. In this video, we'll focus on photolithography as a basic example of light-based lithography techniques. The photolithography technique, as the name indicates, is a process that involves photons for printing features on a wafer. Specifically, the photolithography technique images a structure presented in a lithography mask, as shown here, onto a light-sensitive resist that has been deposited onto a substrate, as shown here. The schematics here illustrates the photolithography process. The image on the right-hand side shows the lithographic mask where the patterns are created on a glass mask. Specifically, the mask consists of the transparent and opaque regions. The opaque regions on the mask block the UV light, while the transparent regions allow the light to pass through. Once the light passes through the transparent regions on the lithographic mask, it triggers specific chemical reactions in the regions of the photoresist located directly below those patterns. The photolithography process involves three main phases. It starts with the design of features that will be printed on a mask. The photomasks are then created using a direct writing technique such as e-beam lithography. Finally, the photomasks are used in an exposure system for printing the features onto a wafer. The smallest feature size that can be printed using a lithography technique is referred to as the resolution limit. When using a light source for performing the lithography process, the resolution limit is determined by the Rayleigh criteria. In particular, the critical dimension, CD, or minimum feature size that can be printed using lithography is directly proportional to the wavelength of photons lambda here. Therefore, the use of light sources that emit photons with shorter wavelengths directly impacts the downscaling of the critical dimensions achievable through the photolithography process. The UV lights emitted from the high-pressure mercury lamps are commonly used for performing the photolithography process in a mask aligner system. Specifically, the high-pressure mercury lamps can generate photons with three wavelengths of 430 nanometers, known as G line, 405 nanometer, known as H line, and 365 nanometers, known as I line. The typical critical dimensions achievable using these photons, for example, G line, is on the order of 1 micron or slightly less. The use of shorter wavelength UV lights, including extreme UV lights, is essential for printing nanoscale features using the photolithography process. The plot here shows the historical trend and progress in improving the printing capabilities of the photolithography systems. As can be seen in this plot, shorter wavelength going from 436 nanometers down to 193 nanometers has resulted in and contributed to the reductions of the critical feature size. However, the considerable improvement in printing smaller features are largely due to advances also in optical systems. Significant advancement in modern optics have enabled printing features as small as 13.5 nanometers. The slide here shows 3 methods of wafer exposure used in photolithography processes. They are contact printers, proximity printers, and projection printers. In the case of contact printers, the mask is placed in direct contact with the resist layer deposited onto the wafer. The hard contact between the mask and the wafer generally results in damage to both the wafer and the resist layer. The proximity printing largely solves this defect issue since the mask and the wafer are kept separate. However, the separation between the mask and the wafer degrades the resolution. The hard and proximity printing capabilities are generally available in simple mask aligners. The dominant method of wafer exposure today is projection printing. These systems provide high resolution without the problems of wafer and mask damage. In projection exposure tools, the mask is typically separated physically from the wafer, and an optical system is used to image the mask onto the wafer. Generally, this optical system reduces the mask image by a factor of 4 to 5 times. As a result, only a small portion of the wafer is printed, as shown here, during each exposure. Therefore, the mask or the wafer must be moved to print the entire wafer. The slide here shows the photos of 3 exposure systems. The image on the left shows the mask aligner system that can support hard contact and proximity printing. This type of photolithography systems is suited for research settings and can provide typically micron-sized critical dimensions. The image in the middle shows an ASML 193 immersion tool. This system can print features as small as 40 nanometers with 1 to 2 nanometer overlay accuracy. Finally, the image on the right shows an ASML EUV system capable of printing features as small as 13 nanometers. These 2 systems use advanced optical systems for printing nanoscale features and are used in commercial manufacturing of silicon microchips. Photolithography is extensively used because it offers fast operation and scalability. Unlike direct writing, large portions of the wafer can be exposed at once, increasing the throughput and improving the scalability of the process for printing on large wafer dimensions. In the next video, we'll provide an overview of the processing steps involved in a photolithography process.